So we're just about to begin the first derivative test, and so we're working on our test intervals. We need to find our test values. Then we're going to label the increase, decrease, and then, oh, I'm sorry, before that it was the sign. So we want the sign plus minus of the first derivative and then the increase, decrease. That's where we get it from. Okay. This is a first derivative test, so that's going to be the sign of the first derivative, of course. And remember that when you're using the first derivative test, you're going to take your first order critical values, which I have up here, and I'm going to use them to partition the domain. So you've got to start with the partitions of this domain. So I'm going to have -1 and 1 as separators as well as the new places. So my first interval will be from negative infinity up to the smallest critical value of -3. Then we're going to go from -3 to -1, partitioning that domain. Then we're going to go from -1 to the next critical value of 0. Then we're going to go from 0 to 1. Then we're going to go from 1 to the square root of 3. And then finally, we're going to go from square root of 3 the rest of the way to infinity. So the original domain was originally 3 places, and we cut it 3 more times. So 1, 2, 3 more splits gave us a total of 6 intervals. Okay, in each of these intervals, I need to find a test value. So I need something smaller than the square root of 3. It'd be handy just to know how large the square root of 3 is. I believe that it is about -1.6. Let's just double check. -1.7. Okay, so I was off by a tiny bit, -1.7. That's going to be particularly useful when I'm going between the square root of 3 and 1. So something smaller than the square root of 3 could be -2. Something between them, so this is -1.7, I could choose -1.5 as something that's between them. Then I could choose -1/2 between -1 and 0. I could choose +1/2. Between 0 and 1, I could choose +1.5. Between 1 and square root of 3, and I could choose 2 as something bigger than the square root of 3. So those are going to be our test values. Okay, next we need to plug them into the first derivative. So I'm going to type my first derivative and then, oops, wrong button of course. There we go. I'm going to type my first derivative and then evaluate them at it. Actually, I'm just going to go ahead and type my original function, f of x, which was 10x cubed over x squared minus 1. And then I'm going to turn the graph off because I don't want the graph right now. And then I can just type in f prime of the numbers I want. So f prime of -2 gives me a value of 4. So I'm going to put, let's see, just a plus in my table right there. I can change that to -1.5. That's minus, it's negative. I'll put a minus right there. Change that to -0.5. That is also negative. +0.5, that is also negative, and then 1.5, that is also negative, and 2, and that is positive. Okay. Alright, so if I look at my table now, I had a whole bunch of negatives in here. So discuss these for a second. First, I'll fill in the increase, decrease. So I've got increasing, decreasing, 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 increasing. Now, for our summaries, if I wanted to list the intervals of increase and the intervals of decrease, we'll talk about which ones we can condense and which ones we can't. So the intervals of increase are going to be from -infinity to the square root of 3 union the square root of 3 comma infinity. Now, these are all decreasing, but I can't just condense them and say I'm decreasing between negative square root of 3 and positive square root of 3 because I have some undefined values right here. So if we remember, the original function was undefined at negative 1 and 1, so those have to continue to be breaks. So I'm going to actually have 3 separate intervals here for decreasing to find around those places where the function was undefined. So we are going to be decreasing from negative the square root of 3 to negative 1. Union, we're going to decrease all the way from negative 1 to 1. Union, we are going to decrease again from 1 to the square root of 3. Okay, so you can condense that into one interval because it is continuous at 0. 0 was a first order critical value, remember? So it was a candidate for an extrema. It's going to be one of those candidates that turns out to not be an extrema because there was no change from increasing to decreasing. Okay, so the next thing that we need to do is classify those extrema. Actually, that kind of gets me to step 6, so I don't do all my steps in the exact same order right here. So in step 6, I have a critical value right here. I'm going to just highlight my critical values real quick. Critical value at negative the square root of 3, critical value at 0, and critical value at the square root of 3. Now, when I change from increasing to decreasing, that's going to be a maximum. When I change from decreasing to increasing, that's going to be a minimum. And then we're going to have none at that 0 value right there. So we have a maximum at x equals negative the square root of 3. And we have a minimum at x equals positive the square root of 3. Now, we could, of course, find those y values. I'm going to find them when I get to the Desmos graph for it, but right now, that ordered pair would be negative the square root of 3, comma, whatever f of negative the square root of 3 is. So we'll deal with that graphically to find that point. Okay, so then I have the square root of 3, comma, whatever f of the square root of 3 is for the minimum. Okay, so that was step 5, part 1, the first derivative test. On to step 5, part 2, the test for concavity. And that's where we're going to use the, again, same kind of table setup. Notice that there was a table, one big table that was in the notes. I'm not using this table because I think it's actually more convenient to do them separately. So even though that's in our notes, I'm writing on the back of my pages now actually to complete these separately. Instead of having my table, see, in this particular one problem, once we find our second order critical values, since this one was 0, we see that there's an overlap in them, and so I can use the same intervals for both, which is why that table was built that way, but that is not usually the case. So usually I would not make one big table, which is why I'm not going to do it right now. In most cases, it's not as efficient to do one big table. So I'm going to keep with what I would usually do in most cases here by setting up these two tables separately. So we're going to look at some test intervals. We need some test values, we need some sign, and this is of the second derivative, and then our conclusions are going to be concave up/down. Okay, and then we're partitioning the domain again, and so the domain is negative infinity to negative 1, and our only second order critical value is x equals 0, so then we're going to go from negative 1 to 0. Then we're going to go 0 to positive 1, and then we're going to go 1 to infinity. So we're partitioning that domain. We only have one second order critical value, that's at 0. The other two splits are things that are not in the domain, so keep that in mind as well. These aren't the same kind of splits. Those were originally there and not the domain, and then the one new split at 0 because of the second order critical value that we already found. Okay, so test values, something less than negative 1, so you can pick anything, say negative 5, and negative 2 is fine, doesn't matter, anything between those, so negative 0.5, positive 0.5, and then 10. I'm just picking any value that I happen to want that fits in the interval, and I'm going to go back over to Desmos, and I can type in the second derivative, so f double prime and we'll plug in our -5, and that gives us a negative value. We'll plug in our -1/2, and that gives us a positive value. +1/2, it's a negative value, and our 10 gives us a positive value. Okay. So there we have some changes, and so we see that we are concave down, concave up, concave down, and concave up. So if we summarize those intervals for our intervals of concave down, just to put them together, we're going to be concave down from -∞ to -1, union from 0 to 1, and we're going to be concave up from -1 to 0 and from 1 to infinity. Then the part 6, which was again the extrema if it was the first derivative test, and the inflection points if it was the test for concavity, is going to be that because we did change sign, we changed from positive to negative, didn't matter what the change was, if it was positive to negative or negative to positive. We did change concavity at the critical value. Remember, you can't have inflection points at places that aren't in the domain, just the critical values. So there is an inflection point at x equals 0, and so its ordered pair would be 0, whatever f of 0 is, which is 0 actually. Sorry. So it's going to be 0, 0, I believe. But that finishes step 6. Okay, that got most of the big calculus pieces out of the way with the derivatives and the tests for increasing, decreasing, and concavity. Step 7 is going to have us looking at vertical asymptotes and behavior. Now, these steps in the project I broke down a little more finely so that instead of having to do step 5 twice and step 6 twice, I think I numbered them separately, so our numbers will vary on those. Don't worry about the numbers, I'm just doing each of the individual steps. And then 7, looking at all the asymptotes. So for vertical and horizontal asymptotes. Okay, so vertical asymptotes are going to be places where the denominator equals 0. And so that's going to be at x equals plus and minus 1. Those are their places that are not in the domain. Remember, that's because the numerator is not also 0 there. We had, I think it was 10x cubed over x squared minus 1 was the polynomial. And so the bottom is equal to 0, but the top is not. The top is definitely non-zero up there. It's 10 and -10. So that means that x equals -1 and x equals 1 are vertical asymptotes. Okay. And then for horizontal asymptotes, there will not be a horizontal asymptote here because the power on the top is larger than the power on the bottom. So for horizontal asymptotes, we'll have none. Power on the top is 1 larger than the power on the bottom, so there's going to be an oblique. So we're going to do the long division to find that oblique asymptote. So x squared minus 1 divided into 10x cubed gives us, need to multiply by 10x. So that gives us 10x cubed minus 10x. And if I distribute that subtraction, that gives us a remainder of 10x. And I already am too small to continue to go into 10x with the x squared. So y equals 10x from the top with a remainder of 10x as well is going to give us the oblique asymptote. So the slant asymptote or oblique asymptote is going to be the equation y equals 10x. Okay, so for now that takes care of the asymptotes. I've got 2 vertical and 1 slant. I can also talk about the end behavior. So if I look at the limit as x approaches infinity, I know it's going to go infinite because there is not a horizontal asymptote, but I don't yet know if it goes positive infinite or negative infinite. So if I look at the 10x cubed over x squared minus 1, and we use the 1 over the lowest highest power technique. Highest power in the bottom is x squared, and that's lower than the higher power on the top. That gives us the limit as x goes to infinity of 10x over 1 minus 1 over x squared. We remember that 1 over infinite, if I plug an infinite in for this infinite on the bottom, goes to 0. So I'm going to be going to infinity over 1, which is going to infinity. If I plug in a negative infinity instead, then as x goes to negative infinity, just write down f of x, we don't need to write down the work. It's still going to be that same ratio, but I'm going to plug a negative infinity in there instead. So a negative infinity on the top over that 1 in the bottom is going to go to negative infinity. So now I know I'm going along my slant asymptote, and I'm going up on the right end, and I'm going down on the left end, because as I go to negative infinity on x, I'm going to negative infinity on y. Okay, so that's the end behavior section. So end behavior. And that was grouped in our chart, remember, with the asymptotes. It asks us to talk about asymptotes and end behavior. Now we're on to number 8, where it's going to ask us to find the intercepts. Okay, so I think we should finish this, and then we'll get to the graphing. So step 8 are intercepts. So we're going to plug in 0, so f of 0, that is 10 times 0 cubed over 0 squared minus 1, that's 0. So that means that your y-intercept is 0, 0. And then for the x-intercepts, if I set the original function equal to 0, that will give me just the numerator equals 0, so 10x cubed equals 0. Again, x equals 0 is the only solution. So the x-intercept and y-intercept are the same point. There's the chance, of course, that you could have more than one x-intercept, but in this case we don't. We just have that single x-intercept. Okay, and that finally satisfies all of the by hand conditions, and step 9 is to start graphing it and compiling these things on the graph. So we're going to do that in the next video.